Sacrificial metal, typically zinc, is attached to a boat's hull below the waterline. When the boat is in contact with water, the zinc reacts with the water and forms a protective oxide layer on its surface. This oxide layer prevents the oxygen in the water from reaching and corroding the boat's metal parts, such as the hull, propellers, and shafts. The use of sacrificial metal is based on the principle of galvanic corrosion. When two dissimilar metals are connected in the presence of an electrolyte, such as water, a corrosion cell is created. The more active metal, in this case zinc, acts as the anode and corrodes, while the less active metal, the boat's hull, acts as the cathode and is protected. Sacrificial metal provides reliable protection against corrosion, provided it is properly installed and maintained. The zinc anode should be connected directly to the hull using a proper bonding system and should be replaced periodically as it corrodes. Firstly, it extends the life of boat metal parts by preventing corrosion. Secondly, it reduces the need for costly repairs and replacements. Thirdly, it improves the overall performance and safety of the boat. Fourthly, it protects the boat's hull from stray electrical currents and lightning strikes. The size and location of the zinc anode will determine the level of protection provided. Sacrificial metal does not protect against physical damage or erosion of the hull. It is important to properly bond all metal components on the boat to the sacrificial metal to ensure effective protection. Zinc anode should be inspected and replaced regularly, typically every 12 to 18 months or as recommended by the manufacturer. If other boats in the marina have improperly attached electrical cords or are not properly grounded, stray electrical currents can enter the water and create a corrosion hazard. Sacrificial metal can help mitigate this hazard by providing a preferential path for the current to flow from the hull to the water, reducing the risk of damage to the boat's metal parts. However, it is important to emphasize that proper maintenance and grounding practices, including the use of proper electrical cords and proper grounding systems, are essential for the safety and protection of all boats in the marina. The concept of sacrificial metal hinges on electrochemistry. When different metals are immersed in an electrolyte, like seawater, they develop varying electrical potentials. This potential difference drives the flow of electrons from the more active metal, the anode, to the less active metal, the cathode. This electron flow constitutes an electrical current, and the process is known as galvanic corrosion. The anode corrodes preferentially, sacrificing itself to protect the cathode. Zinc is commonly used as a sacrificial anode because it is more electrochemically active than most metals used in boat construction, such as aluminum, steel, and bronze. The electrochemical series ranks metals in order of their standard electrode potentials. Metals higher on the series are more easily oxidized and act as anodes, while metals lower on the series are more resistant to oxidation and act as cathodes. Zinc's position in the electrochemical series makes it an effective sacrificial anode for protecting a wide range of metals commonly found in boats. Proper installation of sacrificial anodes is crucial for their effectiveness. The anode must be in good electrical contact with the metal it is protecting. This is typically achieved by bolting or welding the anode directly to the hull or other metal component. A bonding system, which consists of a network of wires connecting all metal parts of the boat, ensures that all components are at the same electrical potential and are protected by the sacrificial anode. The size and placement of the sacrificial anode are also important considerations. The size of the anode should be proportional to the surface area of the metal being protected. The anode should be placed as close as possible to the metal being protected to minimize the electrical resistance between them. Regular inspection and replacement of sacrificial anodes are essential for maintaining their effectiveness. Anodes corrode over time as they sacrifice themselves to protect the boat's metal parts. The rate of corrosion depends on factors such as water salinity, temperature, and the presence of stray electrical currents. Anodes should be inspected regularly and replaced when they are approximately 50% consumed. The effectiveness of sacrificial anodes can be compromised by several factors. One factor is the presence of a non-conductive coating, such as paint, on the metal being protected. The coating insulates the metal from the anode and prevents the flow of electrons. Another factor is the presence of stray electrical currents in the water. Stray currents can accelerate the corrosion of the anode and reduce its lifespan. The use of sacrificial anodes is not a substitute for proper maintenance and grounding practices. Proper grounding ensures that all electrical circuits in the boat are properly grounded and that stray currents are minimized. Proper maintenance includes regular cleaning and inspection of the hull and other metal parts to remove any corrosion or fouling that could interfere with the effectiveness of the sacrificial anode. In addition to zinc, other metals such as aluminum and magnesium are also used as sacrificial anodes. Aluminum anodes are often used in saltwater environments, while magnesium anodes are typically used in freshwater environments. Choice of anode material depends on the specific application and the metals being protected. Stray current corrosion is a significant concern in marinas and harbors. Stray currents can originate from various sources, such as faulty wiring on boats, shore power connections, and underwater electrical cables. These currents can flow through the water and accelerate the corrosion of metal parts on boats. Sacrificial anodes can help mitigate the effects of stray current corrosion by providing a preferential path for the current to flow from the hull to the water. However, it is important to identify and eliminate the source of the stray current to prevent further corrosion. Electrical bonding systems play a vital role in corrosion prevention. A bonding system connects all metal components of a boat, including the hull, engine, propeller shaft, and two hull fittings, to a common ground. This ensures that all components are at the same electrical potential, minimizing the risk of galvanic corrosion. The bonding system should be connected to the sacrificial anode to provide cathodic protection to all bonded components. The effectiveness of a bonding system depends on the quality of the connections and the conductivity of the wires. All connections should be clean, tight, and corrosion resistant. The wire should be sized appropriately to carry the expected current. In addition to galvanic corrosion and stray current corrosion, other forms of corrosion can also affect boats. These include crevice corrosion, pitting corrosion, and erosion corrosion. Crevice corrosion occurs in confined spaces, such as under gaskets or around fasteners where oxygen is depleted. Pitting corrosion is a localized form of corrosion that results in the formation of small holes or pits on the metal surface. Erosion corrosion is caused by the impingement of fluid or particles on the metal surface. Each type of corrosion requires different prevention and mitigation strategies. The principles of corrosion prevention extend beyond boats and are applicable to various industries, including oil and gas, construction, and infrastructure. Understanding the fundamentals of electrochemistry and corrosion mechanisms is essential for engineers and technicians working in these fields. Cathodic protection is a widely used technique for preventing corrosion in pipelines, storage tanks, and other metal structures. Cathodic protection involves applying an electrical current to the metal structure to make it the cathode in an electrochemical cell. This prevents the metal from corroding. There are two main types of cathodic protection: impressed current cathodic protection and sacrificial anode cathodic protection. Impressed current cathodic protection uses an external power source to supply the electrical current, while sacrificial anode cathodic protection uses sacrificial anodes, similar to those used on boats, to provide the current. The design and implementation of cathodic protection systems require careful consideration of factors such as the environment, the metal being protected, and the electrical characteristics of the system. Regular monitoring and maintenance are essential for ensuring the continued effectiveness of the system. Corrosion monitoring is an important aspect of corrosion management. Various techniques are available for monitoring corrosion rates and identifying areas of corrosion. These include visual inspection, electrochemical measurements, and non-destructive testing methods. Visual inspection is the simplest and most common method of corrosion monitoring. It involves visually examining the metal surface for signs of corrosion, such as rust, pitting, or cracking. Electrochemical measurements, such as polarization resistance and electrochemical impedance spectroscopy, can provide quantitative information about corrosion rates. Non-destructive testing methods, such as ultrasonic testing and radiography, can be used to detect corrosion beneath the metal surface. The data obtained from corrosion monitoring can be used to optimize corrosion prevention strategies and predict the remaining lifespan of metal structures. Corrosion inhibitors are chemical compounds that are added to fluids or coatings to reduce the rate of corrosion. Corrosion inhibitors work by forming a protective layer on the metal surface or by neutralizing corrosive agents in the environment. There are various types of corrosion inhibitors, each with its own mechanism of action and application. The selection of the appropriate corrosion inhibitor depends on factors such as the type of metal being protected, the environment, and the operating conditions. The use of corrosion inhibitors can significantly extend the lifespan of metal structures and reduce the risk of corrosion-related failures. Coatings are widely used to protect metal surfaces from corrosion. Coatings provide a barrier between the metal and the environment, preventing corrosive agents from reaching the metal surface. There are various types of coatings, including paints, polymers, and metallic coatings. The selection of the appropriate coating depends on factors such as the type of metal being protected, the environment, and the desired performance characteristics. Proper surface preparation is essential for ensuring the adhesion and performance of coatings. The metal surface must be clean, dry, and free of contaminants before the coating is applied. Regular inspection and maintenance of coatings are necessary to ensure their continued effectiveness. In conclusion, sacrificial metal provides an effective means of protecting boat hulls from corrosion. Understanding the principles of galvanic corrosion, proper installation techniques, and regular maintenance practices are essential for maximizing the effectiveness of sacrificial anodes. Additionally, addressing stray current corrosion and implementing proper electrical bonding systems are crucial for ensuring the long-term protection of boats in marine environments. This knowledge extends beyond boat maintenance and is applicable to various industries where corrosion prevention is critical. By implementing appropriate corrosion prevention strategies, we can extend the lifespan of metal structures, reduce the risk of failures, and ensure the safety and reliability of our infrastructure.